Well, good morning, Complex Gang. Hope you guys are doing well. My family's doing well. We're looking forward to celebrating Monday, Thursday tonight. We usually have a lamb, and we like to read some different passages of Scripture with the kids, and it's really a special time. So we're looking forward to that. Well, I wanted to begin our third lecture series remotely. This will be in the material for homework 12. It's going to be a longer series. So I'm going to give you more time. This won't be due right away, but you want to work through this and work through the book. I'll try to mention the sections that we're covering as well at the end, but starting at around section 60 and then pretty much through the end of the chapter, I think is the plan. So I wanted to do two things today in this lecture series. So one is just to recap some basic facts about power series. So you guys just finished a homework assignment where you went through and worked on some different power series and got to play with the formulas a little bit, but I wanted to make sure that you picked up some of the key facts as you were reading through the material. And then second goal is I want to introduce Laurent series. What is that? Well, that's going to be what we're going to talk about. So first off, one remark. I wanted to make very clear to you something that I'm not sure if the book highlighted or not. I think it might not have actually. But given a complex power series, looks like this, right? There's only three possibilities, and let's write those down together. So the first possibility is, let's actually give myself a little more space. I'm a little tight there. One, the series, it converges absolutely for all z. It converges on the entire complex plane, absolutely everywhere. Okay? That's one possibility. That's kind of an extreme case, although it happens quite frequently. Another possibility is that the series converges only at z equals z naught. That's also an extreme case, although that can happen as well. So here, you only converge at this one point z naught, and that's it. And the third possibility is there exists a real number r, it's positive, such that the series converges absolutely if you're inside the disk centered at z naught, radius r, open disk centered at z naught with radius r, and the series diverges if you're outside that disk, but we're not talking about the boundary here. So on the boundary we can't say, but if you're actually outside that disk, then you diverge. And so this is going to be the situation that we're often going to be interested in. I don't have room for a picture. I guess we'll squeeze one here, but here's your z naught, and there's this open disk around you. And I want to mention just how these three cases, what they have to do with being analytic. So if your function is analytic everywhere, then your series converges absolutely for all z. So if this series represents a function that you know a priori at the beginning is analytic everywhere, then you know the series is going to converge for all z. And so you guys did a lot of examples where you saw that was indeed the case. So here, if you only converge at z naught, there's not a little bubble around z naught where you converge, then you're actually not analytic at z naught. And finally, if this series represents a function that converges absolutely inside this disk and diverges outside the disk, then you are analytic on this disk. And so we'll talk more about that as we go along. But the way the series converge has a lot to do with the associated function, whether it's analytic or not. All right, so that's the first remark I wanted to make. The second remark that I wanted to make has to do with analyticity, I think that's how you say that, and the differentiation of power series. So let's look at the case where I've got this power series, and I'm going to think of it as representing a function. And let's assume that it has a radius of convergence r bigger than 0. So you know that it converges on this disk. All right. So then what can we do? Well, we can say the following. So then f is always analytic on z minus z naught less than r. We said that above, but I'll say it again. And the kind of the key thing that I want to write here is we can differentiate term by term. And so what I mean is, i.e., f prime of z is going to be n equals 0 to infinity. Actually, we're going to lose the first term. We typically make that n equals 1 to infinity. C0 is a constant, so it's gone. So then we're going to get Cn, starting with C1. So Cn, and this is supposed to be an n power up there, in z minus z naught to the n. Hopefully you notice the missing n upstairs. It's fixed now. So we take the derivative, and then we subtract 1. Wow, that was very convoluted. But I think we got everything fixed here. So Cn starting at n equals 1. And then let's see, when you plug this in, yeah, we're good. That's the formula. So this is f prime of z. So let's see if we can squeeze just a little quick example in here. I'm going to be a little tight on space. Let's switch colors. We'll do blue. So we know that, for example, 1 over 1 minus z, I'll zoom in a little bit, is the sum n equals 0 to infinity of z to the n, which you know is 1 plus z squared plus so on and so forth. And this thing is valid for the modulus of z less than 1. So then if you take the derivative, zoom in again, take the derivative of 1 over 1 minus z, you're going to get 1 over 1 minus z squared using your standard calculus formulas. And you can differentiate this series, and you can just say, well, look, that's just the sum n equals 1 to infinity of n to the z, n times z to the n minus 1. And then quite literally, you're just differentiating each term. The derivative of 1 is 0. That's why we lost the first term. The derivative of z is 1. Then you get a 2z, so on and so forth. And again, this is going to be valid for the modulus of z less than 1. So I think I'll break this video here, and we'll continue on in the next one.